Hey Algebra 2, here are your notes for lesson 7.5 where we're going to be talking about operations with radical expressions. So we've already looked at the majority of these simplification techniques, but it never hurts to review them to keep getting better and to just kind of review what simplifying means. So a quick note, you've got a summary up here, but essentially what I want you to notice is the index n is as small as possible. In case you're not familiar with those terms in the box, I'm going to give those to you right here. So we've got x raised to the m power, and n is the root. The n is going to be our index. That's going to tell us what type of root, whether it's the square root, the cubed root, the fourth root, etc. Everything inside of the radical is going to be what we call the radicand. And we've already talked a lot about radicals, but I don't know if we've specifically put these terms to them. So when I'm talking in this video, I'm going to be using the math language, and we need to be aware of that. So, knowing this, the index is as small as possible. We want to make the radical as small as possible. The radicand contains no factors other than one that are nth powers of an integer or polynomial. So essentially, we want the radicand to be as small as possible. It can't contain any fractions, and we don't want any radicals in the denominator. That's pretty standard stuff. So let's see what this looks like. First off, breaking down roots. We've done this a little bit already, but in case you forgot, essentially what I'm going to do here is make a factor tree, and I'm going to try to get a list of my prime factors in order to see if any of them are squares. I would do a factor tree, but what I'm actually going to do instead to make it a little bit easier is I'm going to put all of the factors inside of a radical. So square root here breaks down 27 inside is the same thing as 3 times 3, which is 9, and then 9 times 3, which is 27. So I've just broken it down like this. Now, once it's into its prime factorization, what we're going to do is look for pairs. Because this is a square root, we want to look for pairs that can be taken out of the square root. For example, you've got one right here. 3 times 3 is 9. We know 9 is a perfect square root. So if we bring that 9 out to the front, i.e. we take the square root of 9, we're going to get 3 in front, just by taking that pair out. We are then left over inside of the radical with just a regular 3. It's still the square root there. So essentially we have just found a pair, we've unsquared it, and set it up as a multiplication. And that's all there is to it. Let's see that again. This one's already got a number in front of it, but breaking down the radical itself doesn't change. It's still a square root. 54 breaks down into 6 and 9, which is the same thing as 2 times 3 times 3 times 3. Again, I'm looking for pairs because this is a square root. There's a pair that I'm going to bring out to the front. It's the same thing as 5 times the pair I took out times whatever is left in the radical. In this case, it's going to be 2 times 3. However, we don't want to leave it like this. There's a lot more numbers than we really need, so we're going to simplify. 5 times 3 is 15. 2 times 3 is 6. We can't break the radical down any further. We can't simplify anything outside, so those are our final answers. And the last one here, we've got 24. However, this one is different because it's no longer a square root, it's a cubed root, which means instead of taking out pairs from a radical, we're going to take out triples. So 24 is the same thing as 2 times 12, or 2 times 2 times 2 times 3. Again, taking out triples. There's the triple I'm going to take out to the front. This would be 2 cubed. The cubed root of 2 cubed is just 2. Oop, I should put my 3 there. And then, of course, whatever is left over in the radical, we're just going to leave alone. You don't need the multiplication sign. I just do it for posterity. All right, combining like roots. I think these look a lot more complicated than they are, but I'm going to show you why they're not. Essentially what we're going to do is right now we've got something that is 4x plus 5x squared plus or minus 7x cubed. They're not like because none of their square roots are the same. However, if we take our simplification from this first one and make all of these similar, I bet you we're going to find some of those like roots that would make this problem easier. So the way that I'm going to do this is I can't break down 4 times the square root of 3. But I can break down 5 times the square root of 12. And the way that I'm going to do that is by simplifying as I did before. 12 is the same thing as 2 times 2 times 3. It's a square root, so I take the 2 out to the front. 2 times 5 is 10 root 3. There is a like root that I can now work with. However, because I'm not completely finished, I want to be able to simplify this one as well. It's the same thing as negative 7 times the square root of 3 times 3 times 3. Of course, the 3 can come out, so pair there. That would be negative 21 root 3. So now I can rewrite this problem using things that look more similar. So let's do that. I'm actually going to do that over here. We've got 4 root 3 plus 10 root 3 minus 21 root 3. And I know a lot of people get confused by the roots. Here is my little college hack. So there's something called substitution method. And what that means is I can essentially replace the thing that's bothering me with something that's easier to look at. So in this case, this square root of 3 can confuse some people. How about I say that x is equal to the square root of 3? Then I can replace each of my square roots with an x. And this I'm much more familiar with. 4x plus 10x is 14x, minus 21x is negative 7x. I'm used to that. I can simplify that. And then all I'm going to do is the same way that I substituted x for the square root of 3, I can substitute the square root of 3 for x. So in my final answer, instead of writing negative 7x, which isn't what the problem asked for, I can write negative 7 times the square root of 3. Now, if you know how to combine those like roots, you're totally confident with it, hey, go for it. However, I just want to show you another method that I really enjoy using when I'm learning new topics. So, this can come in handy for more than just roots, so feel free to use it if it seems like it applies. If you have questions about its application, also please ask. I would rather you ask so that we can learn together. All right, rationalizing the denominator. We've looked at this a little bit, but here's a quick refresher. If there's only one root on the bottom, as opposed to 2 terms here, if there's only one term, we're going to multiply that by just that term. Whatever term cancels out the square root. Now we'll see on the back where we're not working with a square root, that's a little bit different. But if it's a square root, it's really nice because we just multiply by that specific square root. What that does is now gives us the square root of 2 times 2, which is the square root of 4, aka these square roots cancel out, and I'm left with just 2. So on the bottom, I have 5 times 2. On the top, however, it's a little more challenging because I have 2 terms, and you need to multiply that square root of 2 times both those terms. Except those are really big numbers, and before I go ahead and multiply, I'm going to bring those down here and simplify first. Let's see if there's a way to make those smaller. Smaller numbers are usually easier to work with, so let's do that. 5 times the square root of 48 is the same thing as 2 times 24. 24 is 2 times 12, which is 2 times 2 times 3. All right, I'm going to look for some pairs. There's a pair. There's a pair, so I'm going to bring those out. That's the same thing as 5 times 2 times 2. Notice I'm doing it twice because there's 2 pairs. So 5 times 2 is 10, 10 times 2 is 20. So 5 times the square root of 48 is the same thing as 20 times the square root of 3. It's a little bit easier to work with. Let's do the same thing with the square root of 25. 75. Not sure if there's an easy way to bring it down. I'll just draw a line here. All right, square root of 75 is the same thing as 25 times 3. I'm not even going to go down into the prime factors because I know that the square root of 25 is just 5. I know there's a pair hidden in there, so I'm going to rewrite it as 5 times the square root of 3. Now if I bring these up and replace the top, I can say that it is the square root of 2 times 20 square roots of 3 plus 5 square roots of 3. Much easier to then multiply into both of those because we're just going to multiply into the radicals. And we're left with 20 square roots of 6 plus 5 square root 6 all over 10. However, we're not quite done. According to our concept summary up above, we do have to simplify fully. You will notice these each have a 5 in them. They're all divisible by 5. So what we can do here is as long as all 3 terms can be divided by it, we can essentially take out a GCF, a greatest common factor. In this case, it's 5. 20 divided by 5 is going to be 4. So I've got 4 square roots of 6. 5 divided by 5 is just 1. So I have 1 square root of 6. And then 10 divided by 5 is 2. Now some of you might be asking, why didn't you just add those on top? We can add just like we did in the last problem. Well, I could have done that, but I wanted to show you that the GCF works this way as well as the simple way that we're used to. Now I am going to add those like I could have done in this step. I'm just going to do it over here instead. All that does is give me 5 square root of 6 over 2, which can't be simplified any further. So that is my answer. All right, moving on to B here. Notice this one has 2 terms. It's a little different. Instead of simply multiplying by 1 square root, we have to multiply by the conjugate, which if this is a plus sign, our conjugate has a minus sign. If this was a minus sign, our conjugate would obviously have a plus sign. But whatever you do to the bottom, you must do to the top. 6 minus 5 root 2. And then it's a game of foiling. In this case, I'm going to do the bottom first because I know it cancels nicely. 6 times 6 is 36. Positive 6 times a negative 5 times the square root of 2. And the positive 5 square root of 2 times the 6 here, those are going to cancel out. So all I really have to deal with is the 6 times 6 and the negative 5 square root 2 times the positive 5 square root 2, which is going to be negative 25 times 2, or negative 50. And we'll simplify that further in a minute. As for the top, it's a little trickier. We've got 1 times 6. We've got 1 times the negative 5 square root 2. Negative 2 times 6, which is negative 6 root 2. And negative root 2 times negative 5 root 2, which is positive 5 root 2. Ta-da! Just like that. Now it's a game of simplifying. We have rationalized it well. We double check our FOIL, and then we're just going to add things. The negative 5 root 2 and the positive 5 root 2 cancel off, so we're left with 6 minus 6 root 2 over 36 minus 15, which is negative 14. All of these terms, this first term, second term, and denominator, all have a 2 in them, so I'm going to divide that out as a GCF, so that I'm left with 3 minus 3 root 2 over negative 7. Notice when I factored out the 2, it did not factor out of the radical. We treat that like a variable, like an x, as I did in this problem up here. So what's in the radical stays in the radical. What's out of the radical we can work with a little bit more. And then obviously if you want to move that -7 up, you could as well. All right, moving on. Roots with variables and products. These are the exact same as what we just did. However, now we're going to add some letters. But this shouldn't change anything, because if we simplify this one, here, let's zoom in for a minute. Oh, that looks a little bit better. If I rewrite this longhand, I'm going to get 2 to the 5th power. I could write that out as 2 times 2, etc., but I'm going to leave it like this. X to the 8th, U4, and V5. And all this says is that I'm looking for triples. And anytime I see a triple, I'm going to bring it out to the front. So for example, in 2 to the 5th, I have 2 to the 3rd hidden in there. There is a triple that I can bring out in the form of a 2. In X to the 8th, there's an X to the 6th, which is 2 sets of triples. So I'm actually going to bring out X to the 2. I brought out 2 sets of X. Okay. 2 triples of X. U to the 4th, there's technically 1 hidden in there. There's 1 set in here. There's 2 sets in here. There's 1 set in there. So that would be U. And there's 1 set, so 3 minus 5, 1 set in here. So I can bring out a V. I have now taken all of the triples out. What that leaves me with inside of my radical is whatever's left over. If I took out 3 2's, that means I have 2 left over. 2 squared is 4. If I took out 2 sets of 3, I took out 6 x's total, so I'm left with 2 still in the radical. Essentially, 8 divided by 3 is 2 times nicely with a remainder of 2. I took out 1 triple from here. When I did that, I took 3 away. I'm left with 1, so U to the 1. And V5, when I took out that 1 set of 3, I'm left with 2 V's left over. And since I'm looking for the cubed root, I can't go any further. Let's see that again with another cubed root. I'm looking for sets of 3. So in this case, this is the same thing as -3 cubed and x to the 7th. When I look at this, I can take out a -3. There's a triple right there. And then there's 2 sets of triples in here, because x to the 3rd times x to the 3rd is x to the 6th with 1 left over. So I'm going to have 2 sets of 3 come out, and I'm left with just a single sad x inside. And that is as simple as it gets. The last one, the only difference is that you have multiplication with numbers on the outside. The way that I always remind myself of how to work with these problems is if it starts on the outside, it ends on the outside. If it starts on the inside, it has to end on the inside. So in this case, when I take 9n squared times 24n, I'm going to put all of that in the radical. However, because I know that I'm going to have to break it down to look for triples anyway, I'm going to break those down into their prime factors. So 9 times 24 is the same thing as 3 times 3 times 2 times 2 times 2 times 3. N squared times n is n cubed. And now I just look for triples because it's the cubed root. I've got a triple of 3. I've got a triple of 2. I don't really know how to indicate that these are a triple. There we go. And then I've actually got a triple of n as well. So there's going to be one of each of those on the outside. So 18 times 3 times 2. And because there's nothing left over inside, we say, oh, there should be an n out here as well. That'll work. The radical goes away, and now we're just left with that, which I don't know off the top of my head. Let me calculate that really quick. I'm going to have to go to the handy dandy Google calculator because I don't have mine available. 18 times 2 times 3 is 108, times that n that we uncubed, we're left with 108n. All right, quick lesson on quotients as well in case you have forgotten. When we have a square root or any kind of radical over a fraction, it's really nice because we can just split that radical up over the numerator and denominator. From here, simplification is basically going to be the same thing. We want to simplify those roots, and then we want to make sure we rationalize the denominator if necessary. I always like to simplify first. That way, if I have to rationalize the denominator, I will, but I may be able to simplify so that I don't have to take that extra step. In this case, I'm looking for pairs. So I see that there are 2 pairs of x cubed, x squared, I apologize. Down here, there is just 1. So I have a y outside and a y inside. In case you're looking and you're like, no, there's only 2 y's there, Burry. Hey, it's okay. What I did was I took out a pair, so I took the square root of y squared, which is just y. I only took out 1 set of y's, so there's only 1. All right, unfortunately with this one, I do have to rationalize, but there's only 1 term on the bottom, so I'm just going to multiply that term by the top and the bottom because I know it'll cancel out that y. The square root of y times the square root of y is y times y is y squared, and then the top we simplify as well. X squared times square root of y over y squared. Can't get any more simple than that. There's our answer. The next one is a little bit tricky, and here's why. When we're taking the square root of something and we have to rationalize its denominator, we just multiply by the square root that we want to rationalize. However, you'll notice in the next one, we're still going to split it up over the denominator and the numerator. But if I multiply this by the square root, it's not going to do anything. I can't take a square root times a fifth root. Well, if I multiply by a fifth root, that's fine. But if I only multiply by 4a, I'm going to get the fifth root of 16a squared, which I still can't rationalize. It still doesn't cancel out those square roots. So what I'm going to need to do is inside of this radical, instead of just putting 4a, I need to figure out what to put in here so that a fifth root times a fifth root cancels out. Now the first thing I notice is that I have 1 4 and I have a to the 1. I only have 1 of each of these things. In order to be able to cancel them, I need to have 5 of each of those things. So when I'm multiplying my roots here, if I've only got 4 to the 1 there, I'm going to need to have 4 to the 4th here, so that when I multiply, I have 4 to the 5th overall, and then I can take the 5th root and just pull a 4 out to the front. Same thing with a. If I only have 1 here, I'm going to have to multiply by a to the 4th, so that once I have done that, I get the 5th root of 4 to the 5, a to the 5, which now I can take the 5th root of and simplify. However, if I had just done 4a, they would not have canceled right. And then, of course, whatever you do to the bottom, you have to do to the top. So we're going to multiply by the 5th root of 4 to the 4th, a to the 4th. When you multiply the insides. So we're left inside with 5 times 4 to the 4th times a to the 4th. But that's not how we're going to leave it, because obviously we did all this work so that we could get that the 5th root out of the denominator. All right, 5th root here. Those 5's cancel, so I'm left with 4a on the bottom. On the top, I have 5 times 4 to the 4. I do have to calculate that. I don't know it off the top of my head. 4 times 4 times 4 times 4 times 5 is going to be the 5th root of 1,288 to the 4th. Now I'm not sure, but I feel like I should be able to take the 5th root of something in there in order to be able to simplify. So let me just look that up because I don't know the 5th root off of the top of my head. Why would I know that? Square roots, cube roots, those are a little more reasonable, but 5th roots are just excessive. All right. I can, in fact, take 5 2's out of this. So I have a 2 out in front. And what I'm left with inside is the 5th root of 40, which can't be broken down any further. Of course, over 4a. However, you should notice that 2 divided by 4 can be reduced into 1 over 2, or the 5th root of 40 over a. That is our final answer. Those problems can be a little bit more to chew, so if you're a little freaked out by those and you need to see some more examples, totally hit me up. I would love to send you some more aids for that. All right, quick thing with different products, if we aren't multiplying by that conjugate, the answer isn't always going to come out nicely. We might have quite a few terms. So in this case, we've got a binomial times a binomial. We can easily just FOIL this one. We're going to be using what we learned up above in this problem here. Outside times outside, inside times inside. So we've got 5 times 2, which is 10. 3 times 3, which is 9. The square root of 9 is then 3. So there's our first term. All right, 5 root 3 times root 5 is going to be plus 5 root 15. Negative 6 times 2 root 3 is negative 12 root 3. And negative 6 times root 5 is just negative 6 times root 5. There are no like roots in this, so we can't simplify any further. However, we can simplify this first number to be 30. So that our final answer is then 30 plus 5 root 15 minus 12 root 3 minus 6 root 5. And that is as simple as it gets. All right. I want you to pause the video here, try these last 4 on your own using the methods that you saw in this video, and then come on back, we'll do them together. All right, hopefully you had a long enough time to pause the video, try those on your own. Let's go through them. This first one, we've got a lot going on here, and all I can say is simplify if you can. So let's start off. What is the square root of 50? Let's simplify that here. Same thing as 25 times 2, so the square root of 50 can be written as 5 times the square root of 2. Negative 4 root 8 is the same thing as 4 times 2, and the square root of 4 is 2, so this is the same thing as negative 8 root 2. Knowing that I've simplified those two things, let's rewrite the problem. 3 root 2 plus 5 root 2 minus 8 root 2. You can use the substitution technique that I showed earlier in the video, or if you don't need it, 3 plus 5 minus 8 is just 0 times root 2, or 0. All right, things with the same roots can be multiplied. Multiply the inside by the inside. I'm going to do the prime factorization while I can. In this case, this is 3 times 3 times 3 times 3, 81. And then 24 is going to be 2 times 2, 4 times 2, 8, 8 times 3, 24. I'm looking for the triples because this is the cubed root. There's a triple. There's a triple. There's what's left over. 2 times 3 is 6. What's left on the inside? 3 times 3 is 9. Why can we not simplify the cubed root of 9? Well, because it doesn't break down nicely into a set of 3. Yes, it breaks down into a set of 2, but we are not looking for pairs in this case. We're looking for triples. All right, this next one is a 4th root, throwing something hard at you, but it shouldn't be too tricky, because if we break this down, it's the same thing as 2 to the 5th, x to the 9th, y to the 5th, and z to the 12th. And because it's the 4th root, we are looking for sets of 4. There is one set of 4 in here. There are 2 sets of 4 in there, x to the 4th times x to the 4th. We've got 2 sets there. We have 1 set here, and we have 3 there. So once I have found how many, I'm going to take those to the outside. 2 to the 1 is 2, x to the 2, y to the 1, and z to the 3. Once I've taken into account each of those sets that I can bring out to the front, I'm going to see what's left over. I only brought out 1 set of 4, so that's 2 to the 1. When I brought out 4 times 2 is 8, there's an x left over. Y to the 5th, when I bring 4 out, there's only 1 y left over. And z to the 12th, there were none left over. So this is my final answer. All right, and the last one, this is one with 2 terms on the bottom, which means we cannot just multiply it by the square root of 3. If we do that, we end up multiplying by this 1, and we still have a radical on the bottom, which is not what we want. So in this case, we're going to multiply by that conjugate, which is just the same thing with the opposite sign. We do that because that is what will allow us to cancel out those square roots. Whatever you do to the bottom, you got to do the top. Let's go to work. I'm going to do the bottom first. 1 times 1 is 1. The 1 and the 3 cancel out. The negative 3 and the 1 cancel out with that. So you have negative root 3 times positive root 3, which is just negative 3. On the top, you've got 2 times 1, which is 2. 2 times root 3, which is plus 2 root 3. On the bottom, you have a negative 2. 2, 2, and negative 2 are all divisible. Here, let's just rewrite this for the sake of space. They're all divisible by 2, so I'm going to factor out a GCF of 2. 2 divided by 2 is 1. 2 divided by 2 is 1, so that's plus 1 root 3. And then negative 2 divided by 2 is negative 1. It doesn't make sense to leave it with negative 1 on the bottom. I would rather just distribute it to each of the top 2 terms, making it negative 1 minus square root of 3. Technically, this term is correct. The way that this is written, this just looks a little bit nicer in my opinion. All right, if you have any questions, feel free to let me know.